Let's do another problem, but before we dive into this, let's go back and ask a fair and straightforward question. If I can shuffle my data and observe how frequently we would obtain our difference in proportions compared to chance, why would I complicate matters by asking how frequently would I obtain my chi-square statistic by chance? Well, it turns out that it comes down to the fact that you can subtract 2 and only 2 numbers. You can't subtract 3 or more numbers. That's not how subtraction works. Okay, with this in mind, let's look at our next example. In this problem, we are looking at about 2,000 records of criminal activity. The records were culled for 3 types of activities: assault, homicide, and robbery. Next, they inquired as to whether or not the perpetrator was known to the victim, someone they knew or a complete stranger. So this data would allow us to explore the question, is there a relationship between the type of crime and whether or not you know the perpetrator? Before we proceed too much further, let's look at this graphically. Here we see that there are many fewer homicides than other crimes in general. The middle column is the thinnest. But we also see that the proportion of homicides committed by someone familiar to the victim is much higher than the other 2 types of crimes. Let's return to the Excel template to continue walking through the analysis of this data. Here's why I can't just calculate the difference between the percentages and then shuffle and do it again. Well, I have 3 percentages in this data. If there were only 2, we could reasonably ask, what is the difference between 46.9% and 21.9%? But once we have 3 or more percentages, the concept of a difference isn't available to us. But I can still ask what the expected frequencies would be for each of the cells in this contingency table. Again, we multiply the column total by the row total and divide by the grand total, and this will give us the expected frequency for each cell in our table. Recall, the expected frequencies are built off the idea that the proportions within each column are the same as the marginal proportions, or in turn, the proportions within each row are the same as the marginal proportions. With this in mind, this would suggest that if there was no relationship between familiarity with the perpetrator and the type of crime, we would expect 803.4 and change for the frequency for assaults by a stranger. Now, in our data, we observed 727. Likewise, we would expect 29.9 and change for the number of homicides committed by a stranger, but we observed only 12. Here, we have the observed counts, and below, here we have the expected counts. And here we have a 3 by 2 table, 3 rows and 2 columns. The nice thing about the chi-square statistic is that it will work regardless of the size of your table. For example, you could have a 17 by 45 table, though I've never seen anything so extreme in practice. But it is possible. You could easily have a 4 by 5 or a 6 by 10 table. You can have bigger tables, which means you cannot even talk about percentages of success versus failures if you have more than 2 columns, as we can do here. In any R by 2, where R is the number of rows, table, in an R by 2 table, if you give me the conditional percentage for one column for a given row, I know what the percentage has to be for the other column in that row. Once you have 3 or more columns, though, you can't just give 1% and know the other values for that row. So the chi-square statistic turns out to be more flexible than just looking at the difference in the percentages. Now, since the complicated approach also handles the situation where we might use the easier approach, well, we'll just decide to always use the more complicated approach. Next, in this sheet, we see that after the expected frequencies, we have the calculations for the squared residuals. We add these all up, and we get the chi-squared statistic of 119.3 and change. And the p-value for obtaining a chi-square this size or larger, well, it is a value with e minus 26. This means we need to move the decimal 26 places to the left. So we are talking about a very, very small number. As a probability, this is very small. Let's step back for a second and walk through the entirety of this NHST. Let's start with the null hypothesis. It would probably be easiest to just do this in words. There is no relationship between the crime and familiarity with the perpetrator. The alternative would be the opposite of this. There is a relationship. Or, stated another way, some crimes are more likely to be committed by people you know than not. Of course, than writing this in words, there are many ways we could choose to state this. Mathematically, we write this as h sub 0 is p sub a equals p sub h equals p sub r, and h sub a equals at least one of these proportions is different. Again, the null is best represented by this mosaic plot, as it shows the same proportion within each column. Now we know the finding, and it almost makes it so that we don't even need to pick a significance level, but we wouldn't have known this before we collected the data. So it is always a good idea to start by quote-unquote setting the rules of the game, i.e. set your significance level at the start of your study. So let's say we had picked the value alpha equals 0.01. In this case, we can write not just that the p-value is less than alpha, but we can use the double less than to indicate how very much less than our value it is. P is doubly less than alpha, or p is extremely less than alpha. Clearly, in a case like this, we reject the null. Thus, some crimes are more likely to be committed by strangers, or some crimes are more likely to be committed by someone you know, than not. Recall, if the alternative is that the percentages are not all the same, then there must be at least 1% that is at least as large as the others. Thus, there must be some maximal value. Thus, our claim is indeed supported, and we can phrase it this way. If it helps, we can also look at this one visually. Here is what the proportions would look like. This middle thin column is the homicides. The right column is the robberies, and the left column is the assaults. What we see is that the percentage within the homicide column, the percentage committed by someone unknown, is noticeably different from the comparable percentages in the other two columns. We are indeed seeing very different percentages. Now, if they had all happened in the same proportion, then this is what the frequencies should have looked like. So the question for the null hypothesis statistical test, the NHST, is how likely are we to see this specific pattern just by random shuffling? Well, here's the results from a simulation. From this, we can see that none of our 10,000 simulations came even close to the chi-squared statistic we obtained. From this histogram, I'm hoping you can see why our p-value was so extremely low. By random chance, getting a result like ours or something more extreme, it is like winning the lottery 100 times in a row. In fact, based on our p-value from the Excel template, we would have to run our simulation 80 septillion or 80 trillion times to see it happen once. To help visualize, 80 septillion gallons of water would fill 120 spheres the size of the Earth. The next thing we will do is look at the next set of chi-square tests. To clarify, the tests we have just been working through are called the chi-square tests of independence. That is, we are exploring, and have been exploring, whether there is or isn't a relationship between our two categorical variables. The other type of test is called the goodness of fit test. The first thing to note is that the goodness of fit test has only one column or one row of frequency counts. It essentially is a very small FDT, a small frequency distribution table. The idea of the goodness of fit test is to ask if the data observed follows some predetermined pattern. That pattern could be uniform in nature, that is each category for our categorical variable equally likely to occur? Or we could impose some specific ratio of how the frequencies might appear. And we can ask if our data supports or contradicts such a distribution among the proportional frequencies. We will look at this next.